The delta H's of formation from which we calculate the delta H of a reaction are typically only tabulated at 298 Kelvin. However, the delta H of a reaction is expected to be dependent on temperature. And so if we want the delta H of the reaction at a different temperature, we're going to need to know how the delta H depends on the temperature. Recall that in general, the derivative of enthalpy with respect to temperature is the constant pressure heat capacity. We are interested in how delta H changes with temperature, but the delta H of the reaction is simply the enthalpy of the products minus the enthalpy of the reactants. And so the derivative of delta H with respect to T is equal to the derivative of the enthalpy of the products with respect to T minus the derivative of the enthalpy of the reactants with respect to temperature. The derivative of the enthalpy with respect to temperature is the heat capacity, and so if we're thinking about the enthalpy of the products, then that will be the constant pressure heat capacity of the products. The derivative of the enthalpy of the reactants with respect to temperature, constant pressure, will be the constant pressure heat capacity of the reactants. The heat capacity of the products minus the heat capacity of the reactants is just the difference in heat capacity for the reaction, and so we can write that the derivative of delta H of reaction with respect to T is equal to delta C sub P for the reaction. Notice the similarity between the derivative of enthalpy with respect to temperature for a single substance and the derivative of the change in enthalpy over a process. We can make this same type of argument for any of the derivatives that we have already derived and apply them to a reaction process, a phase change, or any other process. Now that we have our derivative expression, we can calculate the delta H of reaction as a function of temperature by separating variables and integrating. So d delta H of reaction is equal to delta C sub P for the reaction dt. And so when I do this integral, I'm going to integrate from my standard state, or someplace that I know the reaction enthalpy, and integrate to the temperature at which I want to know my reaction enthalpy. So my right-hand side of my integral goes from T1 to T2, delta reaction, C sub P, dt. Since delta H's of formation are typically tabulated at 298 Kelvin, it's convenient to use 298 as my starting temperature. The left-hand side of this integrated equation is delta H of reaction at T2 minus delta H of reaction at T1, or typically 298 Kelvin. That will be equal to the integral of T1 to T2 delta reaction C sub P dt. If I treat my change in heat capacity of reaction as constant, pull that out of the integral, I will get the following result. There are cases in which the delta heat capacity of reaction is not constant with temperature, and that will result in a more complicated form for this integrated equation.